Welcome to topic 8.3, electric fields, daily video number 2. In this video, we will explore vector fields and symbolically solve for the resultant field at a given location. My name is Eastman Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. Let's look at a vector field map. 2 charges, just chilling, and we have a whole bunch of different dots. Well, at each of those single dots, we could have a vector that's the resultant of the electric fields from the other 2 charges. So if we look at one spot right there in the middle, we have the electric field to the left of the negative one and to the left from the positive one, so they would sum together to equal that. Green arrow also pointing to the left. If we sum up all these things, we might get something that looks like this. A brief note, just for messiness, I did not put arrows on the dots that are right next to the charge because they'd be so much stronger. Because remember, as you get closer to a charge, the electric field increases, not just by doubling, but if it's half the distance, it can be 4 times greater. So that would just make arrows go all over the place. That's why I didn't include those. But for everything else, we get this general kind of shape where they're longer when they're closer, kind of pushing away, and they kind of arc back down around that direction. There's some really fun simulations online that do this automatically. So give those things a whirl if you've never tried them before. So let's see how one of these things happens. If I look at the negative and I look at the positive, I have these 2 different vectors. Well, remember when we do vector addition, we add them tail to tip. And when this goes there, my resultant vector would be that green arrow. So each of those dots that we saw in the previous frame is just the sum of this one's electric field and that one's electric field, and that's our resultant vector. So if we look at 2 that are in line with each other, sure enough, it's pointing to the left and pointing to the left, and the resultant vector is going to be that green arrow. Let's do one more, just to kind of make things a little bit funky. If I'm on the back side of it, this red one's going to be longer because it's closer, pointing towards the negative. And then the blue one, which is much further away, is still pushing away, but it's so far that's going to be shorter. Well, if we shift this one back up that direction, I would expect my resultant vector to be something to look like that. As a brief note, we're not going to draw all the different components when we draw electric fields, because ultimately, all we end up seeing is that one vector. It is the resultant of all the summation or the superposition of all these different fields at that one location. So let's look at an example of how this might work, mathematically for that matter. We have this big red charge here with negative 2q, point charge, and we have this big, or not as big, but smaller blue charge here that has a charge of plus q. They all happen to be some distance d from this point P that exists right here in the middle. And I want to find out what the magnitude and direction of the resultant electric field is at point B, P, due to all 3 of these different charges. Well, let's do one at a time, or all of them at once. We have the blue one going up, the blue one going to the left, and we also have this red one going to the left because we're repelling, or really, if we put a positive test charge there, the test charge goes away from positives, or with the electric field, and it's going to go towards negatives, or still with the electric field, but towards that negative because its electric field is going towards it. So we have these 3 different vectors. Well, if we move them all over here, we can find that the resultant vector would look like that. Again, I'm just adding them together, tail to tip, to find that my resultant vector is just this green arrow. That's what we're trying to solve for. What is the magnitude, the length of that green arrow, and what is the direction or the angle that this has? So let's hop to it. Looking at this thing a little bit more, we have this equation we learned in the previous video for point charges, that the electric field is going to be kq over r squared. This is kind of a reference from our before. If I look at each of these blue arrows, they each have a charge q, and they each are a distance d away. So that's going to be the magnitude of each of those blue arrows. The red one is going to be 2q over d squared, because remember, it was just twice as much charge, but had the same distance away. So looking at this, to find the total electric field in the x direction, it's going to be the red one plus the blue one, to have our total being k3q over d squared. It's kind of nice when the math works out in a pretty way. And if we look at the y direction, it's just the blue one. This bottom charge is the only thing contributing to an upward electric field. So it's going to be the only y component. Well, now I have the 2 sides of my triangle, so I can use Pythagorean theorem to solve for the magnitudes. Take the square root after squaring, and ta-da, if we plug it all in together, we're going to get something that looks like that. Awesome. If we had the number for the charge and the distance, we could plug that in and actually find an actual number. Well, we're not done, because remember, vectors have both magnitude and direction. So where do we get the direction from? Trig. When we look at trig, we're looking at the inverse tangent. Yes, there's a couple different ways you could do this, but I like inverse tangent because we already solved for the opposite, which is going to be our kq over d squared, over our adjacent, which we already solved for to be our k3q over d squared. Wouldn't you know it, that just cancels out to be the tangent, inverse tangent of 1/3, And if we solve that, we can actually get a numerical answer to that one. So even though we don't know the exact values for Q and for D, because everything's all proportional, it kind of cancels out. We know this is going to have this angle above the negative x-axis. Because again, positive x-axis to the right, negative x-axis to the left, and this angle is above that negative x-axis. That wasn't too bad. Well, is there a better way to do this? Sure, you could try to do this experimentally and set this up in the lab and like put two charges there and kind of measure things. What are a couple different ways we could do this? I guess before I not spoil it for you, but if you want to give it a ponder first, what are some ways that you think you could solve for the electric field at every single location? Maybe you've given it a ponder. Well, here's a few different options that you could say that you did. You could use an electric field sensor and put it at every single point and record that value to then get a collection of values. Downside here, if you don't have electric field sensors around, they're expensive to acquire and you have to have the technology to make it work. So maybe there's a little less expensive way. Well, you could hang a piece of pith, which is basically a very light insulator that can accumulate charges to repel and move around and all that fun stuff. So you can do that, but the data might be a little bit noisy. Why is it going to be noisy? Because when you hang it here initially, it's going to move in that field and it's no longer at that location it was before. So you kind of have to like find a way to like look at the angle as it moves. So you might get a general idea. The direction is going to be great, but the magnitude might not work out so well. So what's one other option? Well, unfortunately, it's above our current pay grade for this unit. Unit 9 is the one where you're going to learn about electric potential. And that's probably the best way to kind of set it up, where you could find the electric potential at all these different places using a voltmeter. And you could use the relationship that we're going to learn in future videos to help actually solve for what the electric field would be at that location. But again, these are just 3 different experimental ways you could try to go about this if you didn't want to have to solve for each point, either mathematically or theoretically. So one more thing that we need to cover in this video is something called an electric field line diagram. So we have these vector diagrams that are individual vectors at all these different points. But field lines are just lines that follow the electric field that kind of show general patterns or trends as they connect together. Depending how close they are together, which is, I guess, this thing here as we draw it, as we connect each of these lines, it kind of follows the trend. Everything along this line is going that way to the left. This one kind of goes up a little bit down. You kind of have this symmetry that forms. But those green lines are just representing kind of the sum of what the electric field would be direction-wise pointing. It doesn't tell you how strong. It doesn't give you the magnitude directly. However, it does. Secretly, if you look at how close the lines are together, the closer electric field lines are, the stronger, the greater the magnitude of the electric field at that location. So these, all being close together, are stronger, as you would expect near our point charges. However, in the middle, where they kind of spread out, the electric field gets weaker. And we saw that with our little arrows. That's kind of fun. Brief note that I kind of brushed over before is that field lines can never cross. That would not make sense. That means you'd have one force field summing this way and somehow it sums the other way. So whenever you draw electric field line diagrams, make sure that none of these things cross. This is kind of an overlay of both of them. Let's take those back charges away. And this would be what an electric field diagram might look like. So close together, stronger electric field. And then along the line is which way the electric field is pointing at every single one of those points. Yeah, mine's a little bit squiggly, but if you did this all perfect, you'd have these nice, happy, symmetric shapes. Once again, if you search online, you'll find some really fun programs that can help do this for you for free. So what should we take away from this video? The main thing is knowing how to read a vector field map versus an electric field line diagram. If one of these things pops up, you should know exactly what it is that you're looking at. Also, at any given point in space, there's only one electric field resulting from superposition of all the different electric fields. So it's not this one, this one, this one, this one. It's just all of them tail to tip to sum to find the one resultant vector. And you want to look for symmetry and use that trig to help you solve that effectively. So thank you for stopping by for this video, and I look forward to seeing you in some next ones.